Hello guys, once more. Now we are going to discuss on the simplex algorithm. This is an algorithm to solve linear optimization problems. Of course, we graphed to solve some like a couple of linear problems before. We also took advantage of some other tools to analyze and try to get the solution. But sometimes it becomes just impossible to solve by graphing because the problems have like so many constraints or so many variables to consider. And of course, it's not practical. So this is an algorithm to solve linear optimization problems from that perspective, from a more algorithmic perspective, of course. Consider you have either a maximization problem whose constraints are in this form less than or equal to, or you have a minimization problem whose constraints are in the form of greater than or equal to. If you don't have those two, one of those two standard forms, you need to adapt the problem before considering the solution that I'm going to show you. Okay? Again, this is a method to solve linear optimization problems. Okay? Just to have an intuition, consider you've got like one constraint, linear constraint over here, a second, a third constraint, a fourth constraint, or whatever. What's happening in this algorithm? It's going to visit the corners of our feasible region and verify what is the quality of the solution at that point. So if I want like a maximal or the minimal for that particular problem, I will visit the corner and verify the solution. That's what's going to happen over here. You know what's quite interesting? You see that it builds up like a basis in terms of variables exactly to visit those corners. So let's start. Consider you have this problem. We have a company that manufactures different electronic components. Could be for computers or for whatever. Consider we have like components A, B, and C, and A requires 2 hours of fabrication and 1 for assembling it. B, 3 hours of fabrication and also 1 hour for assembling it. And component C requires 2 hours of fabrication, but it requires 2 hours for assembling it. Of course, considering like any kind of problem, optimization problem we typically have constraints. This company has up to 1,000 hours available for fabrication and 800 hours for assembling. So of course, you guys see this is related to constraints. Consider the profit of each component is respectively $7 for each component type A, 8 for each component under the type B, and 10 for components under type C. So how could I maximize the profit? So I already have like an idea on the objective function after defining this. Just pause the video here, try to come up with the problem, try to formulate the problem, and then you continue, okay? Carrying on. Consider x1, x2, and x3 represent the number of components under the type A, type B, and type C. After that, this is going to be our profit function, aka our objective function in this case. $7 for every piece of A, 8 for every piece component B, and 10 for every piece of component C. So this is our objective function. Now, of course, we need the constraints. First of all, x1, x2, and x3 have to be greater than or equal to 0. We cannot fabricate a negative number of components, of course. That's why, quite simple. Now, we need to think about the other constraints. Remember, we have like 1,000 hours for fabrication, yeah, and 800 for assembling those components into like motherboards or whatever. In that case, remember, the fabrication constraint will be upper bounded by 1,000 because we have 1,000 hours available. And the assembly line, yeah, is going to have like at most 800 hours available. Remember, the number of hours I need to fabricate component A is equals like 2 hours, 3 hours for B, and 2 hours for C. And here the assembling cost. 1 hour for A, 1 hour for B, and 2 hours for C. So those will be our constraints, of course, less than or equal, because I cannot surpass those limits. That's my problem. Take a look. Again, this is a maximization problem whose constraints are in form of less than or equal to. This is the form we're going to work with. On top of that, the first step we need to give is to transform our optimization function, bringing all those terms to the left and making that equals to 0. You're going to see we define a p over here. That's necessary. That's the variable defining profit for us. So we are going to have minus 7x1, as shown here, minus 8x2, minus 10x3, plus p, which is my overall profit. Of course, that is going to be equals to 0. The next step we have to give is we need to add up slack variables into our constraints. So this is our first constraint, this is our second constraint. What happens here? What is a slack variable? Consider we have like just a single component A, a single component B, and a single component C. Of course, in terms of fabrication time, we're going to spend 2 plus 3 plus 2, that's going to be 7 hours, and 7 is less than or equal to 1,000. But I need to add up some slack variable to make this equals to 1,000. So that is a variable to be summed up into my constraint to make it work for the quality. Basically, to ensure we are going to have the solution for the equality and not for something that just like smaller than or equal to, but actually in terms of the quality. So slack variables work exactly like variables to compose our solution and find that particular bound for our constraint or constraints. Of course, here we've got 2 constraints, one slack variable per constraint. So we're going to have S1 and S2. And summing up, eventually, if we are less than or smaller than, if we add up something, we're going to be equal 1,000. If we add up something, we're going to be equal to 800. Of course, S1 and S2 have to be positive, greater than or equal to 0. Otherwise, we're not going to have the solution. That could be negative. Okay? So, of course, those variables will be greater than or equal to 0. S1 and S2. So now we start building what is referred to the simplex tableau. And the simplex tableau is, we started by defining column names. So the names will be all variables x1, x2, and x3. Of course, my slack variables, my p, which is a profit variable, and results. Results are related basically to the right terms, right sides we've got for all those equations. Okay. Next step, we bring all coefficients from constraints. So here we have 2, 3, 2, 1, 1000. And here we are going to have 2x1, 3x2, 2x3, 1s1, s2, 0, p0, and 1000 as a result. Second constraint, 1 for x1, 1 for x2, 2 for x3, that is 1, 1, 2, okay? S1, 0, S2, 1, S1, 0, S2, 1, P equals 0, and results equals to 800, as you see here. Next, after all, we bring the optimization function, the objective function, sorry. Bringing the objective function minus 7x1 will come here, minus 8x2, minus 10x3. We don't have s1 and s2, of course, but we have p, we have 1p, and results equals to 0. Okay? Now, we are going to start solving our problem. How can I solve it? Okay? The first step is we are going to apply the row-reduced echelon form. We're going to reschedule this matrix. We're going to reduce it. That basically to bring the solution. But before reducing, there is something quite interesting. Take a look at this. We are going to use some variable names as row names as well. What is the row name of the first row? That is S1. The second is S2. If you guys consider why we decided to use S1 and S2 here, because S1, if S1 is 1000 and S2 is also 800, our problem will be satisfied and our profit will be 0, because all other variables that don't happen as row names assume 0 as a result. So this is our first solution. Our profit P will be 0. Our slack variable 1 will be equals to 1, as you can see over here. S2 will be equals to 1. As you might see, this is a basis in which we have S1, S2, S1, S2 in terms of columns. So this is our basis matrix, okay, 1, 0, 0, 1, times a vector 1800, and that will become, of course, S1 will assume value 1000 and S2 800. Those two values will satisfy our constraints. You just go back to the problem and verify if x1, x2, and x3 are all equal to 0 and my slacks have those two values, I'm going to have a profit equals to 0, and of course my constraints will be satisfied for the qualities, for the quality of 1000 and for the quality of 800. Next step, this is of course our first solution, initial solution. And of course, from that, as I mentioned, we are going to build up a basis. So B is a basis matrix, okay? Times X equals B as a lowercase b. And of course, my B, my matrix B, uppercase B, will be 1, 1, 0, 0. That is the same as getting the rows and columns related to S1 and S2, okay? Times my vector, which is my result. And that's the result I have for S1 and S2. Now we are going to see that all the steps associated to the simplex method are basically the row reduced echelon form, are basically the ways of reducing my matrix and building up a basis for my problem. That basis, of course, is just built up using algebraic tools, okay? So going on a further step, we go to the last row and select the smallest value, the smallest negative value. It has to be negative, okay? In this case, that is minus 10. This will tell us what is the pivot column. So this column here is our pivot column, the column that we are going to work on. Next, we go of course, we have to select the row, the correct row to work on. The correct row comes after dividing the results by this number that appears over here in my column, which is 2. And here, 800 divided by 2. When I divide both, this will be 500 and this will be 400. I select the smallest value. From this, I will select, of course, this row. So this element over here is my pivot element. That element must be equals to 1 as we do in the row reduced echelon form. So by reducing our matrix, we are going to make this equals to 1. There is something quite interesting over here. After reducing our matrix, this variable related to this row will be substituted by the variable of this column, x3. So this will leave and x3 will come over here. Because we are building up a basis and define which is going to be the variable composing our solution. That's really nice. So 2, we have to divide this row by 2. That's quite basic, okay? Yeah, we're going to divide row 2 by 2, and row 2 is going to assume that result. Dividing, we have this. Half, half, 1, 0, half, 0, 400, okay? Next step, we need to make this equals to 0 and this equals to 0 as in the row reduced echelon form. To make this equals to 0, I just need to multiply the second row by 2 and of course subtract it from the first row. That's written here. Minus 2 times row 2 plus row 1, and row 1 will assume that. Row 3 will assume itself plus 10 times row 2 to make this minus 10 equals to 0 as well. So applying those two simple operations, okay, we're going to obtain, of course, I explained that before, we're going to obtain this 0 and 0 over here. What is interesting now, we just stop now. That's the first step of our reduction. And of course, S2 will be substituted by x3. So you guys see here x3. Now we have a partial solution. What is the partial solution? If I build up a basis matrix S1, x3, considering, of course, 1, 0 in my first column vector, and in my second column vector, I'll have, take a look at this column, 0, 1. My solution would be S1 equals to 200 and X3 equals to 400. At this point, my profit is equals to 4,000. Of course, that's much better than 0 as before. Given a next step, we have a basis now, at least some basis, and that's the basis we have. Okay, just showing you now. You can pause the video and take a look again, guys. Next step, I go for the last row and take the smallest as possible number, and it must be negative. If you only have like positive numbers, you stop. But you have a negative over here, so this is the column related to my pivot element. Next, I need to divide 200 by 2. And 400 by half. Of course, the smallest value will be related to my selected row. In this case, will be, of course, the first row. So going to the next step, of course, it's the first row. Now I need to reduce this element, making it equal to 1, and this as equals to 0, and this equals to 0. To make it, in this case, I just need to divide this row by 2. Yeah, so dividing it by 2, okay, I will have this as my result. And of course, I need to make this element, of the second row equals to 0, and this equals to 0 as well. To make this equals to 0, I need to multiply the first row by minus half and sum up into the second row and assigning it to the second row. The third row will be 3 times the first plus itself, okay, as shown in here in this elementary operation. Next step, after applying those, we will have this. This reduction, just drinking like some water. Of course, now after reducing, we will substitute this S1 by X2. So now we have another partial solution. If we build up 100 elements of X2 and 350 elements of X3, we are going to make $4,300 at the end. Okay? Our basis is x2, x2. This is our first column vector, 1, 0. And the second column vector is related to x3, which is 0, 1. Times this vector, we'll have, of course, the values for x2 and x3. Another basis. Okay. Again, we have a negative element at the last row. So we get it, and this will be our pivot column. Again, we divide 100 by half and 350 by 1/4. Of course, we are going to select this row because this will result in the smallest value, 100 divided by 2. From this, you guys already know that I will substitute the number of components under the type B by components under the type A. Because of this selection. So we are going to make this equals to 1. That's easy. Just multiply the first row by 2. Okay? Multiplying it by 2, we are going to have this solution. And then we are going to multiply this first row by minus 1/4 and sum up with row 2 and assign it to row 2. Row 3 will receive itself plus half times row 1. So we are going to have, of course, 0 here and 0 here. Take a look. Now, of course, we substitute this variable by x1. So instead of x2, we're going to have x1. And you guys can notice that the number of constraints define, of course, the variables that are going to assume non-zero values. Okay, in this case, 2 variables we assume non-zero values. X1, we're going to build up 200 elements under the type component A and 300 elements under the type component C. In total, we're going to make a profit equal to $4,400. Okay. Next step, we're just finished. Okay. Now we just need to interpret the results. It's not difficult to interpret the results. X1 is going to be 200, X3 300. Our profit for 4,400 because I told you before, and other variables that do not appear in my rows will be equal to 0. You know what's nice? Now we don't have slack variables anymore. They don't matter anymore. We have the constraints satisfied for the qualities, just building up components under the type A and C. Of course, type B is just useless in this case because of, again, we don't have a constraint to represent it and to make it necessary and bring it to row names. Quite interesting, isn't it? Finally, we're going to build 200 components under type A, 0 B's, 300 C's, having no slack fabrication time, no relaxation in my fabrication time. No fabrication time will not be no fabrication time will be spared. Basically, we're going to use it. We're going to use all assembling time as well, and this is our profit. Just take a look at those videos, guys. Those are quite interesting. Just pause the video and then you can go for them. Okay? See you in the next video.